Now preparation of haloarenes. Preparation of haloarenes. See the first one given, ESR, electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reaction, benzene or derivatives. Here it is given toluene. Toluene treated with X2. X2 can be, as usual, I used to comment, chlorine or bromine usually. Treated with a Lewis catalyst, iron chloride, iron bromide, AlCl3. Any Lewis acid is taken in darkness, because in presence of light, the reaction mechanism will be free radical reaction, right? So halogen taken, particularly chlorine or bromine, taken in presence of a Lewis acid. So what will be the reaction? You see, suppose we are taking Br2 with iron, you will be getting Br plus. FeBr3 or FeBr2 will be formed, you get Br plus, which is the electrophile. So this combination, or any Lewis acid, Br2 or Cl2 with a Lewis acid, you will get a halonium ion, which acts as the electrophile, and that is attacked by the benzene ring. And since there is already a group present, it depends on this group nature. The existing group will decide, which is so-called a host group. The CS3 group, which is the host group, will decide where the electrophile is getting predominantly connected. All of you know this is an activating group and ortho-para directing group. So the new electrophile may come here, or it may come here, preferably at a para position, leading to extra stability. So X may come at a ortho position or para position. So para product will be generally most stable, all of you know. So if you take chlorine with iron, you get a para chlorotoluene. Or if you take bromine with iron, you get a para bromotoluene as major product. While reaction with the fluorine, many times commented, fluoro compounds are not prepared by this method due to high reactivity, extraordinary reactivity of fluorine. Similarly, reaction with iodine are slow and reversible in nature and requires the presence of some good oxidizing agents to remove the HI formed. Okay, so comfortable reaction led by chlorine and bromine, aromatic electrophilic substitution reaction. Please be very careful about the given condition. That means the halogen given and the Lewis acid given and in the darkness. At the same time, if it is given in the presence of light, in presence of the free homolytic conditions. If it is homolytic conditions, definitely you can think about free radical substitution reaction or so on. Okay. So that's about the first method of preparation of haloarene, which is the very popular reactions of aryl compounds, electrophilic aromatic substitution reactions. Okay. Now the next one, very popular reaction among organic chemistry entirely, that is Sandmeyer's reaction. Sandmeyer's reaction. Many of you definitely remember Sandmeyer's reaction. This is Sandmeyer's reaction. We take an ice cold solution of aniline taken in ice cold condition. The temperature need to be pretty low. 0 to 5 degrees Celsius temperature is maintained, where aniline, this is aminobenzene, aniline treated with sodium nitrite and HCl, or any such mineral acid. All of you know sodium nitrite with HCl. For example, NaNO2 plus HCl can produce HNO2. HNO2, the so-called nitrous acid, which is not so stable, it is always prepared in situ. It is always prepared during the reaction. It cannot be prepared and stored. It is prepared during the reaction time. It is prepared in situ by mixing NaNO2 and dilute acid. Okay. So by mixing NaNO2 and HCl, we are getting nitrous acid, and that nitrous acid working upon aniline, there is a reaction, the so-called diazotization. It is called diazotization. Diazotization, where you get benzene diazonium halide. Benzene diazonium halide. Aromatic diazonium halides are stable only at low temperatures. Okay. While remember, aliphatic diazonium salts are unstable at any temperature. So there is a slight bit of stability. There is a considerable, reasonably good stability for aromatic halides only at a low temperature. That is the main reason why we are maintaining low temperature. So in Sandmeyer's reaction, there are two important things to be noted. We have to ensure low temperature condition. We have to ensure some excess of acid used during the reaction. Aniline should be kept in a low amount in order to avoid some other consecutive reactions. So ice cold condition, low temperature condition, aniline treated with sodium nitrate and HX. This will give you nitrous acid. Nitrous acid work on aniline and you get a special salt, benzene diazonium halide. The structure of benzene diazonium halide, AR for benzene, it is NX. This is minus and this is plus. This is what the structural entity of benzene diazonium salt, AR N2 plus X minus. Okay. Now the reaction proceeds. The benzene diazonium chloride treated with cuprous chloride and HCl, you get chlorobenzene. Cuprous bromide and HBr, you get bromobenzene. Cuprous cyanide and KCl, you get cyanobenzene, and that reaction is called Sandmeyer's reaction. Sandmeyer's reaction. In fact, there are three reactions. AR for benzene, AR N2 plus Cl minus, treated with cuprous chloride HCl, you are getting chlorobenzene. It is treated with cuprous bromide HBr, you are getting bromobenzene, and is treated with cuprous cyanide and KCl. As hydrogen cyanide is a weak acid, we are making use of KCl, you get cyanobenzene. The third reaction is not relevant at the context of discussion, that is why not referred in the NCERT, but the three reactions collectively called Sandmeyer's reaction. Benzene diazonium halide treated with cuprous chloride HCl, cuprous bromide HBr, cuprous cyanide KCl to produce chlorobenzene, bromobenzene, cyanobenzene respectively with the expulsion of nitrogen gas. All three will expel nitrogen gas, and this reaction is called a Sandmeyer's reaction. Sandmeyer's reaction. Right? A detailed mechanism of these reactions definitely we are discussing in our classes, right? And some of you definitely may be knowing the mechanism also. It is advisable to go through, or it is in fact compulsory to go through all the reaction mechanism that is given in the textbook, number one. Number two, there are certain reactions the mechanism is not given in the text, but in a competitive aspect you are advised to refer the mechanism, particularly like Sandmeyer's reaction, how that free radical led through free radical mechanism, how that reaction is proceeded, and what is the story behind benzene diazonium chloride is giving halobenzene, cyanobenzene, etc. It is advisable you please refer if you don't know, right? Many of you may be aware of. Definitely we are discussing in detail in our classes regarding the mechanisms concerned, right? So that is about called Sandmeyer's reaction. So Sandmeyer's reaction, first we take aniline, treat with the sodium nitrate and HCl, we get the disonium salt. The process called diazotization, conducted at a very low temperature in order to maintain disonium salt available. See, we don't prepare disonium salt and store, we prepare only during the reaction because it is not so stable. It is stable only under low temperature, and in fact, if we are talking about aliphatic disonium salt, it is even not stable even at a low temperature. That is the point. Now that disonium salt treated with the cuprous chloride, cuprous bromide, cuprous cyanide, we get chlorobenzene, bromobenzene, cyanobenzene. This is called a Sand-Meyer's reaction. I don't know, some of you whether aware or not, when this disonium salt treated with the copper powder and HCl, you can get a chlorobenzene. That is a modified version of Sand-Meyer's reaction. Or it is treated with the copper powder and HBr, you can get a bromobenzene. This is a modified version of Sand-Meyer's reaction. We call it as Getterman reaction. Getterman reaction. Benzene disonium chloride treated with the copper powder and HCl, copper powder and HBr. We get chlorobenzene, bromobenzene. That is a modified version of Sand-Meyer's reaction. Some of you may be aware of. It is called a Getterman reaction. Anyway, the yield in Sand-Meyer's reaction is pretty high. Okay. And now there is another reaction where this is treated with NaBF4 or HBF4. You get the disonium halide converted to benzene disonium tetrafluoroborate, which is another disonium salt which is pretty more stable, even stable at room temperature. Benzene disonium fluoroborate, benzene disonium fluoroborate, obtained by treating the normal benzene disonium chloride with the NaBF4 or HBF4, you get this. And this upon heating, you can get fluorobenzene. You can get fluorobenzene expelling nitrogen gas and BF3. And the reaction is called a Balsheman reaction. Balsheman reaction. These are reactions which are not there in the syllabus content, but they are very popular reactions which are always discussed along with the Sand-Meyer's reaction. And at least to have a knowledge on at least the choices given, some questions, we can expect some choices, or even the out of syllabus question may come also, we can't say. Particularly for JEE exams and all, advanced or JEE exams, there can be questions. Even though it is not there in the NCERT, the related some reactions, not all, some of the reactions which are closely discussed along with the Sand-Meyer's type reaction which are there in the syllabus, you are advised to just have a review just from the outer periphery of the syllabus as far as possible. Okay, that is called a Balsheman reaction. See, Getterman reaction anyway there in our syllabus. Getterman reaction. Sand-Meyer's reaction in our syllabus. This is also in our syllabus. In fact, I think this is also there in our textbook, I believe. But that named reaction, name is not given. That's all I believe. It is there in the syllabus, not in the current chapter. In the chapter amines, we are discussing these as a reactions of disonium salt. We are discussing in the textbook. Of course, now I remember. It is there in our textbook, but the name is not given. Okay. So all reactions which you can study collectively in one platform, try to review irrespective of which chapter in fact you are dealing with. Try to correlate similar reactions in a unique platform and try to learn together even though they are dealt in different chapters. Okay. So diazotization, Sand-Meyer's reaction, Getterman reaction, Balsheman reaction. Balsheman reaction. And in fact, this can be simply treated with the Ki, you get iodobenzene. That is not a part of any of the named reaction. This is not a part of any of the named reaction. So getting iodobenzene is as simple as that. Benzene disonium salt treated with the Ki, you will get a iodobenzene. That's a detailed coverage of Sandmeyer's reaction. Okay, Sandmeyer's reaction, Getterman reaction, which is a modified version of Sandmeyer's reaction, and Balsheman reaction, preparation of fluorobenzene. I hope it's clear. Okay. So that is about preparation of aromatic haloarenes. Haloarenes. This is what the reaction I've just covered. Yes. You are advised to go through all the reactions concerned. All the reactions concerned. Say for example, this question if you are dealing with, you see the 6th question given. Just taking one question just to give you a triggering effect. 6th question, cyclohexene treated with the bromine in presence of light or heating. Cyclohexene treated with the bromine, heating or in presence of light. You have to understand what kind of reaction it is. What kind of reaction it is? Alkene with the bromine, there can be two possibilities in such a molecule. It can be either electrophilic addition reaction or it can be free radical substitution reaction. In fact, this is a free radical substitution reaction. When you look at light, it is free radical substitution reaction. So where it can be substituted, it can substitute on allyl position, either here or here it can substitute. So one bromine will be coming at allyl position and your product will be like this. This is an allyl bromide. The class of the compound is allyl bromide. What is the UPSC name? 1, 2, 3. 3-bromocyclohexene. 3-bromocyclohexene. Then comes the question, sir, when this bromine is added to double bond, suppose it is given Br2 in presence of CCl4 and it is better to comment dark, right? We can see Br2 will be added across the double bond. This Br2 will be added across the double bond, which is anti-addition. And the product obtained will be like this. One bromine comes like this and one bromine comes like this. You get a anti-product. That means trans product will be obtained, right? So that is electrophilic addition reaction. This is free radical substitution reaction, allyl substitution reaction. So there are beautiful questions in the textbook which you are advised to refer and try to solve as much as possible before dealing with any other questions from various other materials and all. You are supposed to finish all questions from textbook. There are brilliant questions there in the NCERT as exercise question, solved question, example question, in-text question, and even line by line it is very important. There are questions between the lines. There are questions behind the lines. You have to be very careful dealing with the textbook given to you. I'm talking in competitive aspect in particular. Okay. That's about preparation of alkyl and aryl halides. Preparation of alkyl and aryl halides. So many reactions we have gone through, right? From alcohols, from alkanes, and now preparation for aryl halides. Now on to properties of haloalkane, haloarene. Properties of haloalkane, haloarene. Alkyl halides are colorless when pure. They are colorless when pure. However, bromide iodide develop color when exposed to light. What could be the reason? It should be due to greater size of the halide, which gets easily polarized, which can make the absorption of light from different wavelength light. That is the cause of color. Okay. Many volatile halogen compounds have sweet smell also. Regarding melting point, boiling point. You see methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethane are gases at room temperature. Methyl chloride, bromide, ethyl chloride, some chlorofluoromethane are gases at room temperature. Higher members are liquids or solids. Molecules of organic halogen are generally polar in nature. We have discussed that Rx, there is delta minus and delta plus. There is a polarity. Due to greater polarity as well as higher molecular mass as compared to parent hydrocarbon. Greater polarity due to Rx bond. Higher molar mass due to X. Hydrogen is replaced by chlorine. Hydrogen replaced by bromine. Hydrogen replaced by iodine. So the molar mass will be greater. So greater polarity due to Rx bond. Higher molar mass due to replacement with the halogen. The intermolecular force of attraction, there is dipole-dipole attraction and van der Waals forces of attraction, which is stronger in halogen derivatives compared to parent hydrocarbon. Okay. That is why boiling point of chloride, bromide, iodides are considerably higher than those of hydrocarbons. So compared to hydrocarbons, boiling point will be greater. Okay. The attraction gets stronger as the molecule get bigger in size and have more electrons. The pattern variation of boiling point depicted in the figure, for the same alkyl group, the boiling point will be like this. For the same alkyl group, Ri greater than Rbr greater than RCl, Rf. I don't have to tell you why, because iodine greater molar mass. When there is Ri, iodine coming, greater molar mass, 127 or something. Bromine is only 80, chlorine is 35.5, like that. So greater the molar mass, greater will be the molecular attraction because of the increase in size and mass. For Ri, mass will be greater, molar mass will be greater, the size will be greater, attraction will be greater, boiling point will be greater, right? You can see for a particular compound, CH3X, X for chloride, bromide, iodide, chloride, bromide, iodide, chloride, bromide, iodide. You see the variation? Chloride, bromide, iodide. You see the variation? Chloride, bromide, iodide. See, as the carbon increases, size increases, mass increases. So alkyl group, methyl group, ethyl group, propyl group. Molar mass increases, size increases, attraction increases, boiling point increases. So there is an increase in boiling point. For each case, chlorine, bromine, iodide, chlorine, bromine, iodide, chlorine, bromine, iodide, like that. It's beautifully picturized in the textbook. Okay, right? And then another important point, that is a general comment for all organic compounds, all of you know, with increase in branching, boiling point decreases. 375 for a linear chain, 364 there is a decrease, 346 it's all like a globular system, right? It's more branch. So with increase in branching, the molecular attraction decreases, boiling point decreases. Boiling points of isomeric dihalobenzene nearly the same. Para isomer high melting than the others. Para isomer high melting than the others due to symmetry in para position. Look at the melting boiling point of dichlorobenzene. Dichlorobenzene boiling point 453, 446, 448. Boiling point nearly same, slightly higher upper hand over here. Slightly upper hand over here, maybe due to that high degree of polarization, I mean dipole character. Now the melting point is greater over here, 323, because of the molecular symmetry. It's making a close packed arrangement. In the solid state, dichloro, when comes at para position, the molecule is more symmetrical and there is a more effective close packing, which lead to higher melting point. Another important point regarding density also, bromo, iodo, polychloro derivatives heavier than water. Bromo, iodo, polychloro derivatives. You know density of water 1. Chloro derivative 0.89 less than water. This is bromo more than water, iodo more than water, dichloro more than water, trichloro very high, tetrachloro very high. So bromo, iodo, polychloro derivatives heavier than water. Right. See, there can be conceptual questions. giving 2-3 different layers, water given, some of the compounds like this given, which is on the upper side, which is on the lower side, marking X, Y, Z. There can be a question. Chloro, it will be above water. This will be above water, while these components will be below water. They are heavier than water. Okay. The density increases with increase in number of carbon atom, halogen atom, and atomic mass. That's it. That's it. That's it. Now about a talk on solubility also. Solubility also. Haloalkanes are very slightly soluble in water. They are slightly soluble in water. Even though they are said to be polar, they are not sufficiently polar to make a hydrogen bonding, or it's able to break the hydrogen bonding in water. Rx is polar, agreed. Rx is polar, but this is not sufficiently polar to break this hydrogen bonding and thereby create a hydrogen bonding with water. That is not substantially performed. So they are not highly soluble, they are slightly soluble. In fact, you know, they give a turbidity, they form a precipitation. They form a precipitation, right? So the interaction between alkyl halide and water is not that much favorable compared to water-water interaction. That is the point. You see that in order to dissolve haloalkane in water, energy is required to overcome the attraction between haloalkane molecules and break the hydrogen bond between water molecules. We have to break the hydrogen bond between water molecules, and thereby water molecule and haloalkane make an interaction, right? It's creating only a less energy release, when new attractions are set up between haloalkane and water molecules. When they interact, energy released is only less energy. Not sufficient energy is released when Rx interact with water, so that H2H2 interaction is broken and there is more interaction Rx and water. That is not happening. So due to thermodynamic reasons, we can comment, due to thermodynamic reasons, the interaction of Rx with water is not that prominently supported. Because Rx interacting with water, the energy released is less, which is not sufficiently enough to break water-water interaction. Okay, that is the point. So that is the main reason why they are very slightly soluble in water. So that is about the preparation and properties. Preparation and of course physical properties of haloalkanes, haloarenes. Okay. Now our discussion is proceeding to chemical reactions. Chemical reactions of haloalkanes. A detailed study on the three types of reactions commented: nucleophilic substitution reaction, elimination reaction, and reaction with the metals. The three prominent characterized reactions performed by haloalkanes. That is our next discussion. So, number 1, nucleophilic substitution reaction. Nucleophilic substitution reaction. It is also called, it is written as SN reaction. SN reaction. All of you know SN means substitution nucleophile. Nucleophilic substitution reaction. So the existing nucleophile, existing electron rich species replaced by another species. That is nucleophilic substitution reaction. So you can understand an alkyl halide RX is interacting with a nucleophile, which can be represented normally as Nu minus. All of you know nucleophile means electron rich species. So electron rich nucleophile is substituting the existing halogen. So this bond will break and X will be out as X minus, and this nucleophile will be connected to this R part. And the result will be you get RNU leaving X minus. So X is replaced by another electron rich center. This is what nucleophilic substitution reaction. Alkyl halides are, haloalkanes are especially giving this reaction in particular. So one of the characteristic reactions we can say for haloalkanes is nucleophilic substitution reaction, as they are prone to make a heterolytic cleavage over here, giving X minus and R plus will be attacked by a nucleophile. We have to examine all the possible cases involved in nucleophilic substitution reaction, which is enlisted as a tabulated form in the textbook. This tabulated form of reaction you have to go through meticulously one by one, right? For example, the first one, NaOH or KOH. What will be the reaction? Each reaction you have to examine. An alkyl halide treated with the NaOH or KOH in aqueous condition. No doubt, very simple to understand, OH minus will act as the nucleophile. OH minus will act as the nucleophile, replacing X. So X will be replaced by OH minus and the product obtained will be alcohol. So whenever you take an alkyl halide treated with a particular reagent, what is going to be the class of product and what is the reagent and what is the nucleophile? Try to understand with a few examples quoted in the textbook in the tabulated form. So that is number one, alkyl halide treated with the NaOH or KOH, which act as the nucleophile. OH minus act as the nucleophile. So X is replaced by OH minus. Chlorine, bromine replaced by OH minus. Right. Number two, simple solvolysis reaction. Number two, simple reaction. Solvolysis reaction. An alkyl halide is treated for solvolysis. Simply hydrolysis reaction with water. So water itself acts as the nucleophile. You know it is electron rich species. So it will be HOH. This OH will be replacing X and it is a simple solvolysis reaction. Again the result is same. You are getting alcohol. So reaction number one with the NaOH or KOH aqueous condition. Reaction number two, simple solvolysis reaction. So in the first one, OH minus act as the nucleophile. Second one, H2O itself act as the nucleophile. The result is same, right? Third one, hope you remember, very popular reaction. Very popular reaction. An alkyl halide treated with the sodium alkoxide. An alkyl halide treated with the sodium alkoxide. NaX out. And this RO minus will be attacking over the electrophilic center. You get ether, RO, R dash. Very popular reaction. What is the popularity? Exactly. Williamson's synthesis. This is Williamson's synthesis. Preparation of ethers from haloalkanes. Right? So that is third reaction. So reaction number 1, 2, 3. Next, another popular reaction. Few minutes back we were discussing about that reaction. Reaction with the NaI in dry acetone, alkyl chloride or alkyl bromide treated with the NaI in dry acetone, where this chlorine or bromine replaced by iodine precipitating NaCl, NaBr comes out as a precipitate. Few minutes back that reaction has been discussed. Finkelstein reaction. Finkelstein reaction. Halogen exchange reaction. Finkelstein reaction and Schwartz reaction. Discussed a few minutes back. Right. So that is number 4. So number 1 with NaOH or KOH. Number 2 simple solvolysis, Williamson synthesis. And now it is Finkelstein reaction, and now reaction with ammonia and derivatives. The reaction number this. It is Hofmann's ammonolysis reaction. Hofmann's ammonolysis reaction, where an alkyl halide is treated with ammonia. Again, there is a nucleophilic substitution reaction. You get RNH2, a primary amine. This reaction can happen continuous format according to the relative amount of ammonia and Rx being taken. Suppose we are taking excess of Rx. Suppose we are taking excess of Rx. What the result will be? This can again react with the Rx, the obtained product. You will get R2NH, a secondary amine. Suppose it is different alkyl groups, it will be like what you see in the textbook, RR-NH, like this. Same alkyl group means R2NH, different alkyl group will be RR-NH. This is exhaustive reaction. Exhaustive alkylation may proceed, that is Hofmann's ammonolysis reaction, a part and parcel of Hofmann's elimination reaction, which is very popular, right? And now it can again continue. It can again continue reaction once again. As we are taking Rx in excess, you can get R3N, a tertiary amine. Suppose it is different alkyl groups, it can be R-N, tertiary amine. And even it can give quaternary ammonium salt. You can get R4N plus X minus. That is a quaternary ammonium salt. So this kind of reaction is what explained in the other three subsequent examples. Hofmann's ammonolysis reaction. First we will getting a primary amine. Subsequently there is a reaction giving secondary amine. Subsequently again there is a reaction giving tertiary amine, quaternary amine, like that. It happens when you take this excess. Suppose ammonia is taken excess, primary amine will dominate. When ammonia taken excess and if you are limiting the quantity of alkyl halide, primary amine will dominate. If Rx taken in excess, there will be exhaustive alkylation. It may go up to quaternary ammonium salt, and from there, some of you may be aware of Hofmann's elimination reaction. We are actually learning for the competitive purpose, not in the syllabus, but a few times questions came. Okay. So that is about reaction number 1, 2, 3, 4, 5, 6, 7. 7 reactions. Reaction with NaOH or KOH, reaction with water, reaction with NaI, reaction with alkoxide, reaction with ammonia, and a continuous reaction. Next is reaction with KCN. Reaction with the KCN, definitely many of you may be remembering the importance of reaction with the KCN RX treated with KCN. You will get 2 different products. One is RCN and the other is RNC. And this stands the major product. This will be the major product and this will be only minor product. So when KCN react with alkyl halide, you can say RCN is the major product which only commented in the NCERT, but in fact you get 2 products, RCN and RNC, right? And why such a case? Because K plus and Cn minus, you have free Cn minus available. There is a possibility of connectivity. This is a ambidentate nucleophile. This is a ambident nucleophile. What is meant by ambident nucleophile? Ambident means which can be bind from both sides. It may be bind like this or it may be bind like this. There are 2 polyvalent atoms in that nucleophile, that is carbon and nitrogen. It may bind with the carbon, or may be binding with the carbon, or may be binding with the nitrogen. Such a nucleophile is called a ambident nucleophile, right? Hope you remember. So this may make a binding either with the carbon or nitrogen. If it is binding with the carbon, you get a cyanide. This is cyanide. And if it is binding with the nitrogen, it is called isocyanide. Isocyanide. So there are two possible products, alkyl cyanide or alkane nitrile, or alkyl isocyanide or alkane isonitrile, called carbylamine, in which this will be the major product. Why that is a major product? Because this is that's in fact a important question from this chapter. Why when you use KCN, you are getting RCN as major product? That's an important question. The answer is because KCN is ionic. So what? KCN is ionic. So what? When KCN is ionic, Cn minus is freely available, and it can make a binding either with the carbon or with the nitrogen, and carbon-carbon binding dominates. Carbon-carbon binding dominates because of the thermodynamic reasons. Carbon-carbon bonding is much more predominant. That is the reason. Okay. At the same time, if we are dealing with the silver cyanide, suppose alkyl halide treated with the silver cyanide, that is the next reaction probably quoted in the table. If it is treated with the silver cyanide is covalent in nature. Silver cyanide is covalent in nature, and there is no free cyanide available. In fact, this carbon is bonded to silver. Only nitrogen is free at the moment. So again, there are two possibilities. You can get RCN and you can get RNC, but this will be major product. And now why this is major product? Because carbon is already bonded to silver. Nitrogen is free, and a binding of R with the nitrogen, binding of R with the carbon, R with the nitrogen, binding of R with the nitrogen will be predominant. Because carbon already involved in a bonding. It is not ionic. Earlier it was KCN and Cn minus was freely available. Here it is AgCN, which is pretty more covalent, and Cn minus is not freely available, rather it is bonded to silver. Nitrogen is free, carbon is bonded to silver, therefore Rn bonding predominates. This in fact is an important question from the corresponding area of the chapter. Okay. A similar discussion comes, so that's about these two, KCN, AgCN. KCN, Cn minus is the nucleophile and RCN is the major product, while AgCN is the nucleophile. Nitrogen should be connected in predominance and isocyanide will be the major product. A similar discussion comes KNO2 and AgNO2. KNO2 and AgNO2. If we are dealing with an alkyl halide treated with KNO2, a similar story. You can see this is again K plus and NO2 minus. This is an ambident nucleophile. Either you may get a product RNO2 or you can get the product RONO. Either oxygen or nitrogen can make a bonding. Either nitrogen or oxygen can make a bonding with the alkyl part, and the major product in this case it will be this one. This is the major product and this is only minor product. Why? Because the nucleophile is freely available. The nucleophile is freely available. It is available like this, and carbon prefer to bind with oxygen. Carbon oxygen bondage is more preferred over carbon nitrogen bond. Both can make a bond. Both oxygen and nitrogen can make a bond. Both oxygen and nitrogen can make a bond. Here carbon oxygen bonding is RO bonding is preferred. Thermodynamic reasons, the strength of the bond over carbon RN bonding. Hope it is clear. Meanwhile, the same reaction when we are talking about silver nitrate, what is going to be the scenario is just opposite. If it is treated with AgNO2, silver nitrite, this is a covalent system, AgNO2 ONO, covalent system, and oxygen is already bonded to silver and is not completely ionized. So what happens is the free nitrogen will make a bonding, and again you are getting RNO2 and RONO as product, while here this will be the major product, and this is going to be only minor product. So RNO2 will dominate. RNO2 will dominate. Why? Because oxygen is not free. Oxygen is not completely ionized system. It's a covalent system. So nitrogen is free. A predominant bonding between Rn will take place over Ro. I hope it is coming to your memory, which is a very important part of the chapter relating KCN, AgCN, KNO2, AgNO2. The story is similar, only the species changes. So that's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 examples quoted in the text is over. Next is silver salt of carboxylic acid. Silver salt of carboxylic acid, that is also a reaction given. Silver salt of carboxylic acid, REX treated with R-COOAg. Very simple to understand. It's going to break here, minus and plus. It is already ionizing here, Ag plus and COO minus, AgX out. And what you get is R-COOR plus AgX. You get a ester. Ester is formed. The nucleophile is RCOO minus. Nucleophile is RCOO minus, and you get a ester. That is other one. Ester is the product. Then with the lithium aluminum hydride, you get a H, lithium aluminum hydride, alkyl halide, when treated with the lithium aluminum hydride. In fact, it is a reduction reaction. H will be replacing X, and you get RH, alkane. Okay. Now the last one, R-M. R-M is alkyl metal. Alkyl with a metal. This is treated with R-M. Say for example, dialkyl or alkyl lithium. Alkyl lithium, CH3Li, like that. Okay. Alkyl group with the metal. This will be plus part and this will be minus part. This is the nucleophile, and which will be connecting with the R. The product will be RR. The product is something like a Wurtz reaction. It is something like a Wurtz reaction. Of course, the similar to Wurtz reaction, there is another one you might have heard about, Corey-House synthesis. Corey-House synthesis for the preparation of unsymmetrical alkanes, right? So something connecting to that kind of reaction. You can have a nucleophilic substitution with the alkyl group with the metal, where there is a heterolytic cleavage where you get alkyl carbanion. Alkyl carbanion, which act as a nucleophile. Okay. So these are the important examples from the nucleophilic substitution of haloalkanes with the NaOH or KOH, simple solvolysis, Williamson synthesis, Finkelstein reaction, ammonolysis reaction, 3 reactions, KCN, AgCN studied together, KNO2, AgNO2 studied together, then silver salt of carboxylic acid, lithium aluminum hydride, and alkyl metal. Okay, I think how many numbers? 14 examples quoted in the textbook, right? There are a numerous number of cases, important examples quoted in the 14 examples quoted in the textbook. You have to review that meticulously, right? While the next part of the topic is mechanism involved in SN reaction. Mechanism involved in SN reaction. Mechanism involved in SN reaction. In fact, you know, SN reaction happens with two different kind of mechanism. which is one of the most important topic from the entire organic chemistry of 11th and 12th standard, I would say. SN1 reaction and SN2 reaction. There are two-way mechanism happening with the reaction. SN1 reaction and SN2 reaction. SN1 mechanism and SN2 mechanism. So substitution nucleophile, SN1 mechanism, SN2 mechanism is what we are going to discuss next on the topic. Regarding SN1 reaction, see, the reaction is, we have Rx treated with the nucleophile, we get RNU plus X minus. This is what the reaction. Now, how this reaction take place? What is the story behind? As I told, there are two types of mechanism, SN1, SN2. So how is going to be SN1? SN1 will be like this. There is step 1, Rx is polarizing and breaking as R plus and X minus. X minus is leaving and you get a carbocation. Carbocation. That is the step 1, which is slowest step and rate determining step of the reaction. Okay. And now step 2, the nucleophile attack, which is a fast step. Attack of nucleophile, which is a fast step, and you get a RNU as the final product. This is what the mechanism involved in SN1 reaction. First, carbon halogen bond is breaking and you get a carbocation. And second step, that first step, since it is a bond cleavage step, it is a slowest step, and according to the kinetics, you know, the slowest step is called a rate determining step of the reaction. So that is the rate determining step where carbon halogen bond is breaking and you are getting a carbocation. So SN1 reaction proposes carbocation mechanism. And second step reaction, it is a faster reaction, ionic reaction, where the carbocation is attacked by the nucleophile and we get the final product. Okay. So when you write the kinetics of the reaction, R is equal to K into concentration of Rx. This is what the kinetics of the reaction. Because in the slowest step of the reaction, only the concentration of Rx plays a role, and hence it is a first order kinetics. It is a unimolecular reaction. It is a first order kinetics, and hence it is called a SN1 reaction, substitution nucleophile first order reaction. Okay. And the order of reactivity will be in the order tertiary halide, most promoting SN1 mechanism, then secondary halide, then primary halide. This will be the order of reactivity towards SN1 mechanism. Tertiary highly promote SN1. What could be the reason? Simple logic. Tertiary carbocation is most stable, and here SN1 mechanism proposed by carbocation intermediate. So the stability of carbocation decides the chance of SN1 reaction. So tertiary carbocation being highly stable promote SN1 mechanism. Okay. So that is regarding SN1 mechanism. First, carbon halogen bond is breaking in the slowest step of the reaction mechanism, and you get a carbocation, and to that carbocation the nucleophile get attached to get the final product. Okay. So when you analyze the kinetics study, you can see R is equal to KRX, first order reaction, unimolecular reaction. Order of reactivity will be tertiary most prefers SN1 mechanism, primary least prefers SN1 mechanism. Is that clear? What about SN2 mechanism? How is happening SN2 mechanism? Let's have a look at SN2 mechanism. SN2 reaction. Unlike SN1, SN2 happening in such a way that the leaving of halogen and attack of nucleophile happens simultaneously. This is what happening in SN2 mechanism. If you take an alkyl halide in presence of nucleophile, the nucleophile attack the carbonyl center, you know this is delta minus and this is delta plus. This nucleophile attack on the R plus region before carbon halogen bond is breaking. So thereby we get a intermediate transition state like this. We get a transition state like this. Carbon halogen bond, alkyl group and halogen bond starts breaking. Simultaneously the nucleophile attack. Imagine the nucleophile is a strong nucleophile. It may go for SN2 mechanism because nucleophile attack the alkyl center before the halogen is leaving. So it is happening simultaneously. So the breaking of carbon halogen bond and formation of nucleophile carbon bond occur simultaneously, and thereby the net result is this bond will break and this bond will stabilize. You will get NUR. That is the final product. It is a single step mechanism. This involves a single step covalent concerted reaction mechanism. Unlike the previous one where there is a carbocation mechanism, this is not a carbocation mechanism, and you can very well understand the kinetics of the reaction will be R is equal to K into Rx into nucleophile. The concentration of both Rx and nucleophile play a role in kinetics of the reaction. Hence it is a bimolecular reaction, second order kinetics. Previously it was first order kinetics. Now it is a second order kinetics, and hence it is SN2 reaction, substitution nucleophile bimolecular reaction. A change in concentration of both the nucleophile and Rx will result in the rate of reaction. Here a change in concentration of nucleophile does not affect the rate of the reaction because rate determining step, in the rate determining step there is no role for nucleophile. So change in concentration of nucleophile does not affect the rate of the reaction. That is SN1 mechanism. This is SN2 mechanism. SN1 mechanism carbocation mechanism. SN2 mechanism is concerted covalent reaction. Okay, and the order of reactivity will be just opposite: primary, secondary, tertiary. A primary halide dominate for SN2 mechanism. Tertiary dominate for SN1 mechanism. So tertiary halide highly interested in giving SN1 mechanism. A primary halide is giving SN2 mechanism. Secondary may give SN1 or SN2 depending on other conditions. So definitely many conditions that can influence the nature of the mechanism, isn't it? So if it is a tertiary halide, we'll go for SN1. Primary halide will go for SN2. If it is a strong nucleophile, it will go for SN2, like that. If you are dealing with a polar protic medium, suppose you are taking a polar protic medium, it will promote SN1 or SN2. Polar protic medium. Polar protic medium will favor carbocation mechanism, SN1 mechanism, while organic solvents favor SN2 mechanism. Hope you understand. So variety of characteristics of the reactant, reagent, nucleophile, even the medium can influence whether it is going to be SN1 or SN2. Is it clear? Now whether SN1 or SN2, the common reactivity order is already discussed. It will be Ri greater than, Rbr greater than, Rcl greater than Rf. No need to comment about F. It is the order of reactivity. Ri, whether SN1 or SN2, irrespective of whether SN1 or SN2, the order of reactivity will be Ri maximum, because iodine is a better leaving group. Is that clear? Is that clear? Now we need to discuss some stereochemistry involved in SN reaction. Some stereochemistry involved in SN reaction. There is a slight bit of difference in the stereochemistry involved in SN1, SN2 mechanisms. Suppose we are taking SN1 mechanism and imagine the reactant molecule is carbon connected to the groups or atoms A, B, C, X. Quite naturally, you can understand this is a chiral center. This is a chiral carbon. What is meant by chiral carbon? Chiral carbon means a carbon connected to a simple eligibility criterion for chirality. We know simple and general, there are various conditions. A simple general condition, we assume chirality in a carbon center is tetrahedral carbon connected to 4 different atoms or groups. A tetrahedral carbon connected to A, B, C, X. This is chiral, optically active. And it will rotate the plane polarized light towards right or left. All of you know, if it is rotating to right, it is called dextro-rotatory. If it is rotating to left, it is called levo-rotatory. So there is dextro-rotatory, levo-rotatory characters. We call the molecules as optically active compounds. Optically active compounds, optical isomers. And the phenomenon called chirality. This carbon is called chiral carbon. The molecule is said to be chiral. The phenomenon called chirality. This molecule perform chirality. Now imagine this molecule undergo SN1 mechanism. What's happening is the halogen is breaking and is out as X minus. That is the first step reaction, which is the slowest step and rate determining step. And you get a carbocation ABC. This is the carbocation ABC, which is sp2 hybridized planar system. This is sp2 planar system. And now this is attacked by a nucleophile. The second step, fast reaction, attack of the nucleophile. There is something special regarding the stereochemistry aspect. What is something special is the nucleophile Nu minus may be attacking from this side or may be attacking from this side. It can attack both sides of the plane. There is a chance of 50-50 attack. The nucleophile may be attacking from this side, nucleophile may be attacking from that side. So what? So what? Because the configuration will be different. Suppose the nucleophile is attacking from this side. Suppose it is attacking from this side. The product will be like this. This is the product. That means the reactant and product seems to be same configuration. We call it as retention. We call it as retention. This is called retention. Retention means retaining the configuration. Right? Now what happens if the nucleophile attacking from the other side? It's nothing but you will get NUC like this, A, B, C. You can see this and this are opposite to configuration. One is like this, the other is like this. Opposite configuration and is called inversion. It is called inversion. So there is a chance of 50-50 retention and inversion, and the obtained product are, if it is equal amount forming, it is called equal quantity of dextro and levo. If this is dextro, this will be levo. If this is plus, this will be minus, and vice versa. And equimolar mixture of such a sample will be called as racemic mixture. Racemic mixture. Equal quantity, equimolar mixture of enantiomers. What are enantiomers? These are called enantiomers. This pair is called enantiomers. Enantiomers. Enantiomers are non-superimposable mirror images to each other. One look like this, one look like this. They make non-superimposable mirror images to each other. They are called enantiomers. Enantiomers. And 50-50 enantiomeric mixture will be called a racemic mixture. Racemic mixture is optically inactive due to external compensation. the optical rotation given by this molecule will be cancelled by this. That is called external compensation. And the mixture is called a racemic mixture, equal quantity of dextro and levo. This is what happening in SN1 mechanism. So in SN1 mechanism, if you have a chiral center and imagine the halogen goes, you get a carbocation. Carbocation is a planar system, and now the nucleophile it attack from either backside or front side. It is called backside driven or front side driven. It may happen 50-50. 50-50. So if it is attacking from this side, this will be the product. If it is attacking from this side, this will be the product. If you get this attack, this product, it is called retention. This molecule and this molecule, don't you see? They are identical configuration. Don't you see that? ABCX, ABCNU, they are identical configuration. Isn't it? While if you take the other one, ABCX, here you see ABCNU, it is opposite configuration. This is called retention and this is called inversion. There is 50-50 retention and inversion. 50-50 retention and inversion create such a situation, you get 50 this, 50 this. Means equal quantity of this and this. Equal quantity of enantiomers are formed. And that is called a racemic mixture. Racemic mixture is optically inactive due to internal compensation. And this is the stereochemistry aspect involved in SN1 mechanism. I hope it is clear. Then what about SN2? What about SN2? Let's verify what's happening with SN2. That too is very simple to understand. In SN2, the situation, the story is different. What's happening is, imagine you have a chiral system like what we said here, SN2, another molecules, carbon with the PQRX. Imagine it is attacked by a nucleophile and it is SN2 mechanism. What is SN1, SN2 difference? In SN1, halogen goes and you get a carbocation and then the nucleophile attack. What about SN2? Before halogen leave, nucleophile attack. So the reaction will be NuCPQRX. You get it like this. So here you have two-side attack, back seat driven or front seat driven. There it is only back seat driven because front seat is not vacant. X has not gone. So what is the result? The result is now this X is going and this bond will be stabilized and the result will be like this. And that means it is 100% inversion only. Hope you understand. It is only inversion. It is 100% inversion. If you look at the two molecular systems, this is PQRX. Here it is PQRNU. It is inverted system. It is 100% inversion. Is it clear? And sometimes it is also referred as Walden inversion. It is known with such a terminology, Walden inversion. Walden inversion, right? There is 100% inversion. It is said to be like an umbrella going upside down in a strong window. An umbrella going upside down in a strong storm and wind during strong heavy rain and storm happening, and it's going in heavy wind. It's going upside down. You see that? An umbrella hold like this is turning like this. That is called inversion. Inversion. Here what was the scenario? 50% retention and 50%, 50-50 it was. Here it is 100% inversion only. But never try to make a mistake like if this is dextro, that is levo. Not like that. Don't believe if this is one optical rotation, that is opposite optical. Not like that. Configuration is inversion. There is an inversion in the configuration. Right? Never ever try to make a mistake. If this is given as dextro, this can be levo or dextro because these two molecules are different. This is PQR carbon X. This is PQR carbon NU. These are two different compounds. Their configuration is opposite. Not necessarily the optical rotation becomes opposite. It may become opposite or remain the same. That depends on the molecule. Hope you get the picture. Right? So this happens for tertiary amines predominantly, and this happens for primary amines predominantly. For secondary amine, depending on other situations, it may go for SN1 or SN2. Here it will be 50-50 attack, 50-50 retention and inversion. You will get a racemic mixture. Here you get 100% inversion. Here it is SN1 mechanism. Here it is SN2 mechanism. This is first order reaction. This is second order reaction. This is unimolecular reaction. This is bimolecular reaction. This is carbocation mechanism. That is not an ionic reaction. That is a concerted covalent intermediate compound formation mechanism. Right? So almost all aspects regarding SN1, SN2 is discussed. Is it clear? Is it clear? And try to make a review on the optically active molecules and what is chirality, optically active compounds, optically active molecules, right? For a tetrahedral system, that's a general common eligibility criterion that you can put forward regarding the stereochemical aspect of optically active molecules. A very simple example is tetrahedral carbon containing 4 different atoms or groups. 4 different atoms or groups. If you deal with such a molecule, this is optically active. As you can very simply understand, this is CH3, this is carbon with the bromine and there is one hydrogen. This is CH2 and CH3. You see that this is A, this is B, this is C and this is D, A, B, C, D system. This is chiral in nature. So asymmetric molecules are represented or called as chiral. Asymmetric molecules are called chiral. They are optically active compounds. They show optical isomerism, and optical isomerism is experimentally understood by optical experiment using polarimeter experiment. We identify optical activity by using plain polarized light. For example, how do we understand glucose is optically active? How do we understand glucose is optically active? We take a solution of glucose and we pass plain polarized light through the solution. This is called a plain polarized light. PPL, plain polarized light. How do you get a PPL? By using normal light passing through a nickel prism, you can get a PPL, plain polarized light. Now, plain polarized light when passing through glucose solution, you can see the light passing like this, the plane of polarization like this. When the light come out, it's found to make a rotation towards right hand side. It is found to make a rotation towards right hand side. So the light enter like this and comes out like this. There is a right hand side rotation. And such compounds are called dextrorotatory. Not quite surprisingly, glucose is called dextrose. It is dextrorotatory. What is meant by dextrorotatory? The plane of polarized light rotated towards right. Meanwhile, if you take fructose, fructose is optically active. Many biomolecules are optically active compounds. Almost all biomolecules. Glucose is optically active. The plane of polarization of light will be rotated towards right. Fructose is optically active. The plane of polarization of light will be rotated to left. Hence it is called a levulose. Glucose is called a dextrose. Fructose is called a levulose. Like that. So this is a general criterion for simple organic molecules. If you have a carbon with 4 different atoms or groups, that carbon is called a chiral. That carbon is called a asymmetric carbon, chiral carbon, that perform optical isomerism. They will form non-superimposable mirror images to each other. They will form non-superimposable mirror images to each other. If you take lactic acid, for example, this is lactic acid. This is lactic acid, and this carbon is chiral center. You can see this is A, this is B, this is C, and this is D. 4 different atoms or groups. 4 different atoms or groups. It will have non-superimposable mirror image. It will make a non-superimposable mirror image. You see that the 2 molecules will make a non-superimposable mirror image, and they are called enantiomers. If you take this mirror image and try to place over this, it will make a non-superimposable mirror image. That is what the meaning. It makes a non-superimposable mirror image, like your hands. Our hands are typically example for non-superimposable mirror images, like this. Such molecules are called optically active compounds, optical isomers. And that non-superimposable mirror images to each other will be called enantiomers. These are called enantiomers. Enantiomers. If this is dextro, this will be levo. If this is plus, this will be minus. Dextrose means rotating the plane polarized light towards right. Levulose will be the molecule which rotates the plane polarized light towards left. Levulose. And equimolar mixture of these two will be called a racemic mixture. In case of SN1 mechanism, since it undergo front seat and back seat attack simultaneously, we are getting racemic mixture. Not necessarily 100% racemic always, but still racemic mixture is obtained. While in SN2 mechanism, it is only backside attack, we get 100% inversion, but never try to make a misconcept. If the reactant is dextro, product is levo. Not like that always. It may be or may not, because the 2 molecules are different, but the configuration is opposite. If one molecule configured like this, the product will be configured like this. The reactant configured like this, product will be configured like this. There is 100% inversion. While in SN1 mechanism, 50-50 inversion and retention. Right? And that's about the story regarding SN1, SN2 mechanism. You can easily understand looking at these images. This is chiral system. This is achiral system. You can see the object and mirror image. They are superimposable. Object and mirror image. They are superimposable. While object and mirror image, they make a non-superimposable mirror images. That is what called chirality. Such molecules are said to be chiral. There are beautiful exercises given in the textbook which you can go through. And now the next topic that we are going to discuss is elimination reaction. Elimination reaction. Elimination reaction. Another important discussion from the chemical properties of alkyl halides. Elimination reaction.